So now we will move on to the next talk of this session, where we have Professor Jason Hein joining us today. So Jason is a professor at the University of British Columbia and adjunct professor at the University of Bergen in Norway. He completed his PhD with Phil Halton at the University of Manitoba in 2005, and then he moved on to become a NSERC PDF fellow with Barry Sharpless, and then Senior Research Associate with Donna Blackmont at Scripps Research. In 2011, he started his independent research program at the University of California, joining the University of British Columbia in 2015, where he was promoted to full professor in 2024. His work is in automated kinetic reaction analysis, where he has advanced the reaction discovery and optimization, yielding key mechanistic insights into catalytic processes. His work has also received many awards, including the ACS Young Investigators Prize in 2015, the NSERC Discovery Accelerator in 2021, Killam Teaching Fellowship in 2025, and the RU Lemu Award in 2025. I hope I pronounced that well as well. So please help me welcome Professor Jason Hein with his talk on real-time data and modular robotics for scalable workflow automation. Thank you.
So thank you very much for the invitation, and thank you also for Ram. Perfect setup for what we're working on. The work that Andy Cooper's lab and team is really a huge inspiration to everybody in the field, and it's really a privilege to be able to speak in today's session. Yeah, Ram set up the concept of what we're trying to do very well. So there's a large degree of overlap with the kind of goals and targets that he articulated. As a quick introduction, my group, fundamentally, I'm a physical organic chemist. Well, that just means we're spending a lot of our time trying to understand reaction mechanisms and understand the kind of inner workings of a reaction. Now, that's led to certain things like deeper understanding of rare catalytic behaviors, things like creating new processes like telescoped reactions, where we can take one process directly into the next one, but also understanding and exploration where certain product distributions are possible just by understanding what catalysts are doing and what your opportunities are. All of this is hugely data intensive, and exactly what Ram said, these are expensive reactions, not just the materials you're working with, but the time. So finding ways to automate that and bring in both automated platforms and autonomous platforms is critical, just because it helps to focus and accelerate a huge part of this important research. Today, I'm going to talk heavily about our work, not just in the automation part, but how we're trying to work towards this general concept of what's been termed a self-driving lab. And really, this speaks to the autonomy piece that Ram brought up. So as he broke down every one of these automated workflows, and they've been around for a while as well, they require this kind of three major component. It looks exactly like the normal scientific process, where you have sort of a design, make, test kind of a cycle. Really, when you're talking about an autonomous system, you need something that has the capability to run a reaction. So this is the reactors. This is the actual vessel that the reaction happens in. So you can think of this as the main cookware. You have to have your analytical toolkit. So this is how the thing is actually scored, or what the outcome of it is. And this can be things like HPLC, mass spec, profilometry, really any type of analytical kit to measure the properties or the value for what we're trying to do here. And then finally, some kind of an algorithm that's going to actually do the outcome. Now, my group really focuses on these two. So the reactor design and automation part, the analysis and integrating these, where we partner very heavily with groups that do more of the automation and planning kind of part. For anybody who's looking to learn a little bit more about this space, these are just two recent reviews that I would focus you to. So this first ChemRev article talking about self-driving labs, the material space, written by the Asper Guzik group, is a great sort of touch point. Interesting thing about this field is, while this is actually fairly recent in 2024, things are moving very quickly. So, but it's a good sort of grounding part on that part. Second, too, is the work by Taylor Sparks. Taylor is an amazing educator and visionary in this space, and he's done a lot of work talking about not just the big picture about self-driving and autonomous platforms, but also what minimally viable versions of this is to help democratize adoption and access. So just in general, though, what we have to do, or this concept of closed loop automation, again, while it's really seen a huge boost these last couple of years, this is not new. This is something that groups like the Jensen Group has been working on since 2010. And even back before that, people like Steve Lay have been the pioneers in this kind of adoption of automation in this kind of space. So this is really something that goes has been fundamental to a lot of the sort of adopting or early adopter and innovators. And really what you're seeing now is more integration with these bespoke systems is starting to pervade across others' parts. So the kind of access to really good consumer electronics has really helped to drive adoption from a specialty, more niche thing into something that you're starting to see very broadly. Now, one of the things that we were part of was one of the early sort of on-deck closed-loop optimization. So this is actually the opposite version of what the Cooper Group focuses on. Instead of trying to take legacy kit and then adopt it with a mobile robot, we focused a lot more around designing and customizing more structured decks to do these kinds of optimizations. So what this was is our demonstration in 2021, where we rebuilt a custom ChemSpeed deck and then allowed it to drive via an algorithm and then actually score and actually outcome processes using a data science tool package. So what this was kind of our first foray into how to take a ChemSpeed and do slow batch Bayesian optimization. But and exactly what Ron brought up, the problem with this is it takes a lot of time to customize the deck to do the exact chemistry that you're looking for, but also then the code and the hardware to control it in a field and a system that really wasn't designed for this kind of application. So this is where we stepped back and said, okay, the opportunity from this particular screen was an autonomous batch screen for a hit, in this case for a Suzuki reaction. And the interesting outcome of this one was that we were able to identify very stereoselective and very reactive conditions where the robot itself tested and guided itself to the right kind of ligand, the right kind of outcome, where it's doing that sort of selection and optimization. And again, the challenge here, though, is this is a small well. It's a little vial that says this is a possible condition, but then you're left with the problem of moving forward and scaling this up. And this is really the field of process chemistry and process engineering, where we have to take these kind of early hits and then move them through. And that is a whole other series of challenges. So it's really within this lens that we've been working. I'm part of what's known as the Acceleration Consortium. This is the Canadian equivalent of what you guys are working through in the Alchemy Consortium, where it's an AI, robotics, and chemistry team here in Canada, hosted in the University of Toronto, where we have created multiple domain-specific systems. In particular, SDL7 is the one that I'm mainly focused on, which is the scale-up and process optimization one. So information and hits coming from the other SDLs, such as the small molecular organic or medicinal chemistry ones, we would take those kind of hits, focus on those, and figure out how possible scale-up and optimization could be done, which is its own part. Now, in this concept of scale-up, the real name of the game here is data and observation. So I'm actually from Winnipeg, Manitoba. If anybody has ever visited there, my dad likes to say that it's colder in Winnipeg in January than Mars. So it's wonderful off the plains. This is a common sight you see in the winter, where it has snowed overnight and somebody has just barely scraped off the window here. Now, not only is this a really bad idea, it is actually illegal. But what happens is effectively you get this very narrow keyhole view of the reaction. And because of that, decisions you may make, in this case of like driving under those sort of conditions, are limited by what you can actually see and observe. So this is why this real-time analysis, especially in the context of something like a self-driving lab, seeing information quickly allows you to make good decisions, which allows you to get to outcomes. And this really helps to optimize our most precious resource, as Ram sort of described, which is really the time that goes into sort of setting up and running these experiments. Now, in an optimal world, I would love to be able to have a reaction and have a instant view of what that profile looks like. The reality, though, is that the reactions themselves are complicated. They are not really built to be directly compatible with our analytical kit. And anybody who has experience with this knows this, that running a synthetic reaction often has things like solid liquid slurries, extreme temperatures and pressures, air and water reactive materials, which means that if you want to see inside that reaction or grab an aliquot or do an analysis, you may actually compromise the reaction and ruin it. So your outcome of that reaction is now being tainted by your ability to analyze it. But on top of that, the analysis itself is complex because the material has to be transformed. There's another chemical step to take something from a reaction and prepare it, dilute it, or otherwise derivatize it so that it can be analyzed by what tool you're actually hoping for. So this is where there's this middleware of automated sampling and automated analysis that has to be done to really fuse these two worlds. And this is back to one of those superhuman type abilities. So what you're doing here is saying that the sequence of steps that you would have to do to very carefully and precisely measure something and do this without compromising the reaction requires a layer of automation that has to be built out. Where the name of the game here is to absolutely do this analysis where at no point in time the chemistry knows that we were ever there, right? We want to be able to do this completely stealth without changing the outcomes of the reaction. What's really good about real-time analysis too, if anybody hasn't had this ability, so this is an example of the kind of readout we get from a single reaction. So this is a profile for online HPLC. We get moment-by-moment details of a reaction happening by this HPLC readout. And what you get is not only the major and minor components, but if we, let's say, ran this reaction and we didn't expect to see what's going on in the baseline, we can actually mine for data, mine for trends and pieces that were not really part of our original analytical objective. Having real-time data allows you to sort of focus on the concentration changes of your starting materials and your products, which gives you that level of like, okay, I'm finding something that has a major outcome or a good conversion. But it gets these very small pattern details such as byproduct distributions or intermediates that we're forming that you may not have expected you'd even have for visibility. So having this real-time analysis allows you to go back in history, replay the reaction, and actually pick out subtle details, which is exactly what tools like ML is really good at. Now you can actually take this very highly featurized data set and learn from it. So back to that concept that if every reaction takes 16 hours, I want to make sure that one reaction gives me the most information I can possibly get so I'm making the best decision. So across this space, there's really three buckets we have to sort of address. The first is the preparations. We have to be able to run reactions and do sort of things like analysis, starting material generations, stock solution generations. There's a whole bunch of mise en place and analytical preparation that must be done up front. Then there's the automation execution itself, running the reaction and monitoring it. That's a whole other sort of ballpark that we have to be able to do and have eyes on. And then finally, especially in process chem, getting a data point in a small well is not good enough. You need powder on a filter plate, or you need liquid in a vial. Like this needs to physically make the material, and that isolation purification is something else that we have to bring into the automation framework. So talking briefly about each of these, I want to show you a little bit we've done to sort of address or at least talk about some of the challenges here. So in the preparation space, this is an example of something that we participated in. As it happened back in 2024, British Columbia launched a decriminalization initiative. So what this meant is that possession of certain opiates and controlled substances was no longer illegal. Again, sale was, but the goal was to sort of say, to destigmatize potential possession and use in order to address the illicit drug and the toxic drug crisis that we're seeing in the West. Now, what this means is you need to be able to measure or know what's in a substance that might be something that a user is taking. In other words, it's possible that an enterprising individual thinking that, hey, I can now potentially distribute this with a low criminality, there's an initiative here to say, well, I'm going to cut this with some unknown substance or potentially even sell something that isn't actually what it was sort of branded as. So we needed the ability to do basically a community-facing analysis. We wanted to give people the ability to walk up to a kiosk, hand over a sample, and do the very complex analysis of preparing the sample, running it on HPLC, and getting data out of it. But that whole process is an expert system. And this is where we built this robot whose job was to carry out the normal transformations and steps necessary to take a powder sample, dose it. In this case, they would have a bar-coded pre-weighted vial, and there the person could basically drop off the powder in the pre-weighed vial. It would weigh the difference between the two, so we know how much mass is in the system. It would carry out liquid handling operations to dissolve the material. For anybody who's watched One Punch Man, The name of the terrible tornado, that's the name of that little vortexer at the back, built by Clark, a fantastic mech engineering student that worked with us. So that vortexes and dissolves the material. It's then passed over to a little custom centrifuge where we spin down any insoluble materials, and then it carries out a series of dissolutions where it's dissolving the dissolved component, carrying that over to a sample, prepping them for HPLC, so it's walking the concentration down at different levels, and then it's going to be able to take that sample. The hole cut out in the deck actually allows it to access a commercial HPLC injector. So we're using the standard HPLC auto injector in below to do the injection. The liquid samples then run on HPLC, and then we get the actual outcome. Just as a quick note as well, all the videos that I have on here too, I'm not going to go through them in total detail because a lot of them are a lot longer. But if you're interested in seeing them, we do have a YouTube channel that you can watch and can refer to these points too. So once again, like and subscribe. It would be wonderful for our lab. What you get from this is an outcome that's sort of, a programmatic sort of distribution. In this case, it's HPLC distributions of the components where we can build standardized methods and standardized calibration curves. So on the top, what you see is a series of standards of cocaine, ketamine, bromonazolam, and fentanyl. And the sample in the bottom was submitted with a caffeine internal standard, and this was supposed to be a sample of bromozolam, but you can see there's a small amount of fentanyl adulteration in this particular sample too, as well as cocaine and a little bit of ketamine. So this is democratizing access to information is what the goal was here. But on top of that, back from the lab-facing one, this means you can take a user operation like calibrations and quantification and pass the samples over to the system, and it can run it autonomously. So you come back with fully quantified and calibrated HPLC samples. So this is where you already have the HPLC. One thing I want to note is there's this other process of developing the HPLC method to begin with. Now, this is, again, an expert user is usually involved, but groups such as the Born group at Leeds has shown ways that you can actually use Bayesian optimization to go around that cycle and have the system auto-optimize for an outcome, which would be better separation. So it can actually generate an HPLC method that actually separates those peaks. So we adopted that method. We built a Python version of the wrapper, now known as PyChemStation, which is available on our lab GitLab. It allows you to autonomously control the Agilent HPLC using a macro command sort of structure if you're using the ChemStation CDS. So this allows us to not only do the concentration manipulation, but potentially set up and actually find optimized conditions for our HPLC. Long term, what we're hoping to do is actually be able to go from a structure to not only a concentration mapping, but also property mapping as well, using things like ChemProp and other else. And this is something we're building as we have our database advancing. Moving to the second one, reaction monitoring. Now, this is something that my group has been doing for a very long time. And like I say, we focus on automation in the space to get mechanistic information. So here's a quick example of a CN cross-coupling where the observation was something really weird, where if you actually go in with a higher concentration of palladium loading, you're getting very good stereo retention at this center here. So your product is forming the CN bond, but this center is coming in with the same chirality that you start out with. However, if you drop the palladium loading, very strangely, you start seeing epimerization at this center over here. So there's something that's kind of stereoprotective about your concentration, your catalyst, and that's not part of an active center. Turning our tools loose to this, the first thing we did is actually create a really detailed concentration profile. So we can actually watch the time course profile of a reaction. Now, interesting thing about this one is it's actually done in a heterogeneous solid liquid slurry. And we have a tool that goes onto our end of our probe that allows us to do this kind of reciprocal filtration, sample capture, and then filter cleaning. So every cycle, what we're doing is actually this kind of aspiration and then blowing that solid off. So it means that we can sample through very viscous slurries, the supernatant over time. What we get from this is a profile that shows that, yes, at high concentration palladium, we see good conversion to product with very, very low levels of our stereo inverted product. However, as we drop the catalyst loading, we see not only slower reaction kinetics, but also now this rapid epimerization higher than what we're seeing at that point. So we recapitulated the problem. The nice thing about having this online analysis, though, is this goes back to this time course thing. If you imagine doing an autonomous development where you're saying, find the best reaction, the joke amongst sort of organic chemists is that there's really only 3 time points people care about during screening. So there's basically overnight, over lunch, and over coffee. And again, this is just an efficiency thing. We have so many different parameters to look at in terms of solvent and conditions and catalyst and ligand that you usually compartmentalize and say, I will do a 96 well plate screen, and I'm going to hold the time constant across that point. Now, the problem is if you look at that and say, which one of these conditions or this particular reaction, if you look at those different time points, and I want, let's say, my purple species, this guy here, to be my major outcome, well, over coffee, things look great. Over lunch, well, it's second. And then overnight, it's now not only last, but it's actually degrading. When you actually look at the full kinetic profile, this is actually what's under the hood. It's not just a simple concentration over time conversion. You're seeing everything from rapid conversion, decomposition, sigmoidal kinetics, where after a reaction is done, a new reaction sort of kicks off. And you really need this comprehensive data set that's not just these, zero order or first order assumed profiles to really understand what's happening. When you've got this full picture, you can make good decisions about what to do to fix it. In this case, what we saw was that when is really, really important. So if we have this time course profile, you can see good conversion to our product. And then right here, when the starting material is gone, that's the point where we start to see this decomposition and epimerization. So epimerization is not a problem in this reaction until the reaction hits its full conversion. So it's this after effect part. So you effectively have done a great job, but if you did a high throughput screen, looked out here, you would be potentially concluding that these conditions are not optimal, when really actually you just have to stop it at the right time. It also gives us a perspective of why this is happening. So this is where we dig back into that baseline of the online HPLC. And what we can do is actually see the xanthos palladium oxidative addition complex. This is a catalytic intermediate which forms in palladium systems. We can see it build up and run steady state for the reaction. And right at the end, when you've exhausted your aryl bromide, it tanks, because what's happening is the palladium-2 is now being fully converted to our product. You get your palladium-0, and only then, once that palladium-2 complex has been fully exhausted, is you start to see this epimerization event. And it turns out what's happening in this particular system is that the palladium-2 species is really acting as a Lewis acid protective material for the sensitizers, acting as a sacrificial sequestration agent for the X ligand, or the strong base ligand. And we can prove that out by actually going back and building a new hypothesis that says, well, what would happen to this epimerization event if I have protective palladium-2, in this case, just palladium-2 acetate, and I go through a dosing experiment showing that in the absence of palladium-2, I add base and I get more rapid epimerization. But in the presence of palladium-2, I can actually hold off epimerization up until the titration point where the concentration of my base exceeds the amount of palladium that I happen to be adding to the system. So this is a good confirmation of this particular hypothesis. And again, all of this has been enabled by having automation to give us this complex analysis. But you can imagine pathways like this as being the hypothesis generation and testing engine that goes into the fully autonomous lab eventually. Now, another quick function too is we can take those exact same pieces of hardware, the same online HPLC piece, the robotic separation I showed you for the drug development, drug checking piece. And the really cool part about the systems that we built out is they're modular, which means I can take the same arm, liquid handling harness, and those other unit operation pieces, plus other custom part, and turn it to a fully different application. In this case, we're looking at stochastic antibody drug conjugation. So here is an example where what we have to do is this cycle of taking an antibody. We carry out a reaction which opens up the thiol bridges. We do a functionalization with a certain linker and a certain drug component to come up with what's called an ADC, or an antibody drug conjugate. And the way this is done stochastically is you end up with like a bell curve of how many antibodies or the antibody is decorated by a certain number of warhead drugs. And that ratio, what's called the DAR, the drug antibody ratio, is critical for sort of titrating the efficacy of this material. For certain drugs, even though that adding it to the antibody dramatically reduces off-target activities or toxicity, some ADCs that have these really, really high DARs where they're very, very heavily decorated become super toxic in the body just in general. So you have to actually carefully tune every single particular drug and particular antibody to a certain set of conditions to get the exact DAR ratio that's perfect for that specific cancer target combination. So this is a massive space to search for every new antibody, linker, and drug conjugation. So we built a system taking those off-the-shelf pieces that we had before, which is now just a filter shaker, a liquid handler, the arm, and now what we've added is this custom automated vacuum filtration system. So what we can do is these small volume manipulations and purifications. In this case, where we're using a solid prep. Putting that all together, not only can you use the HPLC as your outcome target, so we're targeting a certain DAR ratio as measured by HPLC, so we're doing manipulation and variation of those conjugation conditions, but we can also use the, like we talked about in the HPLC example, we can use the outcomes of things like gravimetric measurements or telemetry from the reaction to actually optimize how the platform behaves. So for example, this was a custom vacuum filtration system, one of a kind. It requires us to sort of pull a certain amount of vacuum at a certain rate. We have to do certain manipulations like how fast do we dose that liquid. There's basically a sort of a dexterity element of how this particular new piece of automated kit even behaves. Now, because we can control things like the liquid handling capability, how fast it actually moves, and all those other components, you can actually do a closed loop optimization on just how the robot works with this new piece of technology in order to optimize its behavior. So what we can do is actually go through and make sure that it's working appropriately to the kind of outcome we have, which then means that the data we get off it is far more dead center for what we're going to be doing. So very quickly, I want to move to the last part, which is this automation and workup. Now, this is something we've been focusing on much heavier recently, and it's something that we've got a couple of good examples. In particular, this is work being done by fantastic postdoc, Maria, who's building out what's called the purification deck. So this is actually a bidentate system where we've got a shared HPLC, the sort of valuable instrument resource, with two different arms and two different parts of this deck. Over here is liquid extraction, and over here is crystallization. So these are two fundamental sort of workup purification things we have to do in the space. Once again, we can take those modular components, remix them to do very different kinds of behavior. So we can take solids and measure things like a solubility of those solids in different components and mixtures. We can also run a cooling crystallization, like an impurity rejection or some of the other sort of parts. What this lets us do is to use, again, the HPLC as a scoring metric to say, how do I actually look through this large design space of what type of solvent, how quickly do I cool it in order to achieve a certain kind of outcome, such as a crystal impurity rejection or something like that, which would be necessary for a workup purification step. On the other side of the deck, liquid extraction, we can take the outcomes of our reactor, so after reaction is completed, and we can pass it into a standardized EasyMax. Think of this as just an automated benchtop reactor. And what we've done is we've outfitted it with a camera that sits here at the front that looks through that window. And it's viewing in that space to come up with a visualization of what's going on with this biphase. So what we do is we take the space, we've got a light, and we've added this kind of patterning in the back. What that lets us do is add a CV model that does a really good job of measuring where that liquid-liquid split is for a clear sort of biphasic component. So adding these other visual elements and then training the library against that allows it to do this automated visualization for is the sample well mixed? How fast do I have to stir it? How fast is my split time? It also gives us a readout of where those two layers are. So layer volume becomes something that we can measure for doing things like coefficients of split. So this is where the system can actually execute this workflow where we take an outcome of a reaction, we set up a bilayer, we do liquid handling, we do the split and then measure the split time and also split quality. So these are things like, is it precipitating? Do I have an emulsion? How do we get a bilayer or a rag layer or even a trilayer, a triphasic system? Or is it homogeneous as there's no layer between them? Those become a rejection that we go through, and we actually can evaluate the concentration of material in the top and bottom layer using this custom liquid handler that we have over here. We call it the mobile liquid handler. Not mobile like awesome mobile robot, but something that can be gripped, moved, and then controlled by the arm itself. So it's a wireless battery-powered needle, effectively, with a Z gantry that allows us to go through and sample from either the top phase or the bottom phase of a reactor. Those go be prepared to be our HPLC, and those can be evaluated for those two composition points. And those can be carried through, again, a closed loop for optimizing the liquid extraction characteristics. So the last thing I just want to quickly mention, though, is that even if we have good automation and analytics across each of these spaces, we're still left with the problem of access. So this is something we've started to do within my context of my adjunct professorship at University of Bergen, and now an expansion of some work that we're doing with Seoul National University. So we now have, platforms we built in Vancouver that have to be used by chemists at different sites, so Bergen or Korea, sometimes with different languages. So we code in English, but the people using it and scientists using it in Korea are speaking Korean. And we have to have this bridging across gaps. Now, some people that have played around with language models have realized that they're fantastic at context training, pattern recognition, and then basically translation. So what we have done is things like this application where we've shown that we can actually take a JAX protocol, pass it through a trained language model, and actually come up with the input parameters and input files necessary to run something like an EasyMax, an expert system that maybe somebody isn't been trained at. So this acts as a bridging thing where we can actually not just translate English to another language, but English to machine access. So this is a first step towards showing how language models can be used to just democratize the ability to use these very complex systems that maybe you weren't trained at. So it helps to augment your skills in that capacity. The second one, though, is a wrapper. As you've seen on our point, we use many common pieces of the deck, but those each sort of purpose-built pieces of automation is a remix of the hardware that we have, which means we're constantly changing what the decks look like. So the same system, which could be purification, the antibody-drug conjugate, a flow chemistry reaction, or liquid extraction, even though they use common elements, we need this custom orchestrator at the top of it. And this is something that one of my senior scientists, Ivory, has been building out. So she's created this tool known as IvoryOS, which is kind of a pick and place, drag and drop GUI for doing these kind of reorchestration. So it's very good in the early days of building these automation platforms to try out new workflows, especially with a lot of custom equipment. What's really cool about it, though, is we're now expanding it to include things like, again, language models. So she's built out a plugin for the MCP protocol that takes her plugin, the IvoryOS framework, and plugs it into a tool like Claude. So what's nice about this is now somebody can sit down with a language model in the native language, or again, natural language conversation, say, well, wait a minute, what is this platform? What do you do? Hey, but this is the kind of experiment I want to do. And you can actually have a conversation with the intermediate software and then down to the deck itself. So I see this as a huge enabling tool that means chemists that with very little automation expertise can leverage these components in order to bridge and then sort of break into these more custom workflows without having a dedicated training in that capacity. So really with that, again, I really want to thank everybody for the time today. I know it's a very kind of high level sort of overview. I'd really appreciate any other questions and comments. And again, I'm always available to talk and follow up with anybody else. So once again, thank you so much for the time today.